Alright, welcome back. In the last chapter we covered discrete probability distribution, including the binomial probability distribution, Poisson, and hypergeometric distributions. You learned that a random variable can be classified as either discrete or continuous. In most instances, the value of a discrete random variable is determined by counting. But there's also many situations in which the random variable of interest is continuous rather than discrete. A continuous probability distribution can be used to approximate the distribution of possible outcomes for the random variables. The approximation is approximate when the number of possible outcomes is large. Chapter 6 introduces three specific continuous probability distributions of particular importance for decision making in the study of business statistics. The first one of these, the normal distribution, is by far the most important because many applications involve random variables that possess the characteristics of the normal distribution. In addition, many of the topics in the remaining chapters of this textbook dealing with statistical estimation and hypothesis testing are based on the normal distribution. Here are the key learning outcomes for Chapter 6. So after this series, you should understand how to convert a normal distribution to a standard normal distribution and calculate values of the random variable associated with specified probabilities from a normal distribution. We will also cover uniform distributions and exponential probability distributions. Let's begin with normal probability distribution. This distribution is unimodal, symmetrical distribution where the mean, median, and mode are equal. The distribution is asymptotic, stretching either minus infinity or to positive infinity. The normal approaches the horizontal axis. The height and spread is also determined by the amount of variation. Here we can see what a typical normal distribution looks like. All normal distributions have the same general shape as this one. However, they can differ with their mean value and their variation depending on the situation being considered. Again, take note that with this distribution, the mean, median, and mode are all equal. This image shows three normal distributions with different centers and different spreads. Note the total area, or probability, under each normal curve equals 1. Since the normal distribution is symmetric, each half of the distribution is equal to 0.5. This will be useful later when we start performing calculations. Be sure to pay attention to the effects of changing the mean and standard deviation. Changing the mean shifts the entire distribution left or right, while changing the standard deviation increases or decreases the spread. To graph the normal distribution, we need to know the mean, mu, and the standard deviation, sigma. Placing mu, sigma, and the value of the variable x into the probability density function, we can calculate the height, f of x, of the density function. If we try enough x values, we can then construct curves like those shown in the previous slides. The area under the normal curve corresponds to probability. Because x is a continuous random variable, the probability, p of x, is equal to 0 for any particular x. However, we can find the probability for a range of values between x1 and x2 by finding the area under the curve between these two values. A special normal distribution called the standard normal distribution is used to find areas or probabilities for all normal distributions. The trick to finding probabilities for a normal distribution is to convert the normal distribution to a standard normal distribution. A normal distribution has a mean equal to 0.0 and a standard deviation equal to 1.0. The horizontal axis is scaled in z-values that measure the number of standard deviations a point is from the mean. Values above the mean have positive z-values and values below the mean have negative z-values. To convert a normal distribution to a standard normal distribution, the values x of a random variable are standardized as outlined previously in Chapter 3. The conversion formula is the difference between the x value and the mean divided by the standard deviation. This scales any normal distribution axis from its true units, such as time, weight, dollars, volume, so forth, to the standard measure referred to as a z-value. Any value of a normally distributed continuous random variable can be represented by a unique z-value. Positive z-values represent corresponding values of the random variable x that are higher than the population mean. Values of x that are less than the population mean will have a corresponding z-value that are negative. Remember, a z-value is a unitless value indicating how many standard deviations away from the mean the particular value is. If x is distributed normally with a mean of 100 and a standard deviation of 50, the z-value for x equals 250 is 250 minus 100 divided by 50. This means that the particular x value is 3 standard deviations above the mean. The standard normal table in Appendix D provides probabilities associated with many different z-values. The standard normal table is constructed so that the probabilities provided represent the chance of a value being between a positive z-value and its population mean 0. When using the table, begin with the row. This shows the value of the z to the first decimal point, followed by using the column, which gives the value of z to the second decimal point. The intersection of the row and column yields the resulting probability from z equals 0 up to the desired z-value. Remember, it's symmetric, so negative values have the same probabilities as positive values. So suppose we calculate a z-value of 0.52. Using the table, we find 0.5 on the left in the rows and 0.02 on top in the columns. The intersecting probability is 0.1985. Alright, so here we're given a mean of 8.0 and a standard deviation of 5.0. We want to find the probability of x being greater than or equal to 8.0 and less than or equal to 8.6. So we standardize the two values. We see that our mean results in a z-score of 0, and an x value of 8.6 is a z-score of 0.12. So we can convert the probability to a probability of z-score, where z is greater than or equal to 0, but less than or equal to 0.12. So the resulting probability here is 0.0478 for the shaded region under the curve. Here's another example. So this time we want to find probability between 8 and 7.5. So we can see with a mean of 8 and a standard deviation of 5.0, an x value of 7.5 gives us a z-score of negative 0.10. The probability from z equals 0 to a z equal to negative 0.10 is equal to 0.0398. And here we want two shaded regions on either side of the mean. So we want to find the probability of the curve between 7.5 and x 8.6. So in this instance, we'll standardize both x values. So we'll get a z-score of negative 0.10, as we saw in the previous problem, and we'll get a z-score of 0.12. Adding the individual probabilities, 0.0398 and 0.0478, equals 0.0876. You'll need to calculate each individual probability in this case, since on either side of the curve. And here we want one entire side of the curve, the left side of the curve, and a small portion up to x less than or equal to 8.6. So in this case we got a z-score of 0.12 with a probability of 0.0478. And since we have the whole left side of the curve, we'll add 0.5 to result in a 0.5478 probability for a probability of x less than or equal to 8.6. And here we want the opposite. We want a probability of x greater than or equal to 7.5. So we find our 7.5 z-score, which is negative 0.10. The probability associated with that is 0.0398. And since we're looking at greater than or equal to, we'll add the whole right side of the curve of 0.5. So the resulting probability for that whole area under the curve is 0.5378. And now we want x less than or equal to 7.5. So the z-score that we found associated with x equals 7.5 was negative 0.10. So the probability associated with z less than or equal to negative 0.10 is the whole probability of that half of the curve, 0.5, minus probability between z equals 0 and z equals negative 0.10. That probability is 0.0398. Since we're working from the mean outward, we deduct that from the 0.5 to get a probability for our x less than or equal to 7.5 of 0.4602. In this case, we're looking for a probability of x greater than or equal to 8.6. So we're going to do the same thing. Take the whole area of the curve, 0.5, and subtract out the probability associated with x less than or equal to 8.6. And that corresponding probability is 0.0478. So the overall probability for x greater than or equal to 8.6 is 0.4522. And on one final note, in Chapter 3 we introduced the empirical rule for probabilities with bell-shaped distributions. For the normal distribution, we make this rule more precise. Knowing the area under the normal distribution curve between plus or minus 1 sigma, plus or minus 2 sigma, and plus or minus 3 sigma provides a useful benchmark for estimating probabilities and checking reasonableness of results. Go ahead and open Excel file drugs, and let's answer the following questions. Alright, so let's create a frequency distribution and frequency histogram by using the same methods we've done in Chapter 2. Alright, so we can see that it's not perfectly mound-shaped, but the histogram does appear to be approximately normally distributed. Sampling error could be attributed to part of this imperfection. We'll cover that in Chapter 7. Okay, so now we want to simply compute the mean and standard deviation for the sample data. So we'll do that by using our average function, and since we're dealing with a sample, be sure to use the .s, and there are the mean and standard deviation. So for the last part, we're going to assume that the sample came from a normally distributed population, and the sample standard deviation is a good approximation for the population standard deviation. So now we want to determine the probability that a randomly chosen transaction would yield a price of $2.12 or smaller, even though the population mean was $2.51. So this says we want to find the probability that x will be less than or equal to $2.12. And to find this, I'm going to use the standardized function in Excel to find our z-value. Our x here is $2.12, and we can reference the mean and the standard deviation. So we have a z-score of -4.01. So we can rewrite that by saying we want to find the probability of z being less than or equal to -4.006. So we can find the probability using the norm.dist function of z less than or equal to -4. So out on this lower tail leftward, our x value would be $2.12 with the mean equal to $2.51 and a standard deviation of 10 cents. And we will do true for cumulative since we are working with the lower left tail. So cumulative up to the $2.12. So we see the probability is essentially 0 for a drug price less than or equal to $2.12.